In this video, I'm going to talk about tolerances of position. So there's 6 videos in this GD&T series. We've talked about form tolerances, orientation, runout, profile. What all of these tolerances do, for the most part, now there's always exceptions, is control the surface of a feature. So if you put a flatness tolerance on the surface of something, you're going to run an indicator or run a CMM probe over it to determine whether that surface is within the tolerance zone or out of the tolerance zone. Similar thing with runout, right? You're going to rotate a part and check to see if the surface is located to the axis of the datum, and you're seeing if the surface, the form of it, is circular or cylindrical, depending on the runout tolerance. Now, if we used profile on something like a hole, we can locate the hole and control the form and control the size. But what we're doing when we do that is we're controlling the high points and the low points of the hole. Let me show you what I mean on the board. So this is a limited drawing, of course. We've got what we need for this explanation. We've got a profile of a surface applied to a hole. Now, of course, it's going to be a basic dimension in this case. We've got 3 datum features and 3 datum references. So what this gives us is a tolerance zone that follows the true profile of the hole. Since it's 3-dimensional, you essentially have 2 concentric cylinders that are located to A, B, and C. It's perpendicular to A and then located to B and C. So what that would look like is something like this. Okay, so you've got tolerance zones where the part has to fit within. So if the part doesn't come in perfect, you could have variation, but you're still looking to make sure none of the points are outside of these tolerance zones. Now this can be tricky to check without a CMM, because the implication here is that you need to go inside of this part and make sure none of these low points exceed the tolerance zone of the profile. Now, position is going to work a lot different than this. What position does is separate out these low points that are essentially not functional, right? Nothing is going to mate to these low points. If you put a pin or a bolt or a screw through this hole, it's really only gonna, the high points here, and when I say high points in a hole, I mean these points here, right? What would make it the smallest hole, okay? Position is only gonna worry about these points. The lower points are controlled by the limits of size. So they still have to be checked, but you're just not checking them in the same way you would for a profile, right? Now, one thing position does is separate out the location of the feature from the size. So say you had a hole that needs to take a ground pin and have a very tight fit, but it doesn't matter so much where it is. You can do that with position, where it'd be more difficult to do that with profile and certainly more expensive. And then the other way as well, you could have a really tight location and then a really loose size tolerance if that was necessary. So let me show you what I mean by only controlling the high points, how we're going to accomplish that. We're going to use the concept of the actual mating envelope. We've got another figure on the board. Again, not a complete drawing, missing the basic dimensions, but it has what we need. Now, instead of profile here, I've got a size dimension, a position feature control frame, 3 datum features, and 3 datum references, okay? So I've kind of cheated, this is the drawing, and then this is the part that actually comes out, but it's instructive for what we're gonna do here. So how do we decide whether this is within the tolerance zone? So the tolerance zone for position is a diameter, right? We got a diameter symbol here of 30 thousandths, located at the true position, which in this case, even without basic dimensions, we'll get to that later, is going to be on the drawing right where the center mark is. So that's our tolerance zone. Because it's related to datum A right here, that's what gives it perpendicularity. So we're going to project it over here That's our tolerance zone for position. So what are we controlling exactly? Well, for a hole, we're controlling the axis of the unrelated actual mating envelope. What does that all mean? Well, in order to figure out where the axis of this hole is, we need to decide how we're going to get the axis. And the ASME standard, how we're going to do it, is by using the actual mating envelope, which is, for right now, we're going to say it's outside the material. It's the largest similar feature that will expand within a hole, or the smallest external feature that contracts about around an external feature. So in our case right here, how it's usually done is you go through gauge pins until you find the largest one that will fit through the hole. If it's a large bore, you might need something like a mandrel that actually expands into the hole. But essentially what you're doing is trying to find a best fit with these high points and then the largest cylinder that will fit through there. So you'll end up with something like this. Okay, so imagine we went through our box of gauge pins and we found the one that will fit through just barely, and it won't wiggle around, and then the next size wouldn't fit. That's our actual mating envelope. The axis of that is going to be the axis of the feature, right? Because we only care about these high points, because when this part goes into service, those high points are going to be what's going to stop something going through the hole, whether it's a pin or a screw or a bolt or a mating part. So if we imagine, and I'm going to draw it solid, the axis, actual mating envelope, is the axis of the feature, and now we're just looking to see if that entire axis falls within the blue here, our tolerance zone. Now, it's really not that difficult to do on a plate, and I made a whole other video about it. Essentially, you're going to measure from here, take half of the gauge pin, go down, and you'll find a point. You'll do the same thing on the other side. You'll take the worst, do a little bit of trigonometry, which I'll show toward the end of the video, and figure out whether it's within tolerance or not. But that's the big difference between position tolerances and basically all of the other tolerances, and that's why some people have difficulty with it, because you're not really measuring all of the feature. You're only considering what really matters, and it's a very powerful thing to apply to a drawing. And then later in this video, we'll get to applying MMC and LMC and how you can get even more tolerance with this concept, okay? So let's get into some of the nuts and bolts of position tolerances. Now, a position tolerance can be applied to two things: a feature of size or a bounded feature. Bounded features are rarely used, and I'll just touch on it, but a feature of size is used all the time. They have two major characteristics. The first being they're going to have a plus or minus tolerance. Now, it's not always with the dimension. It could be, referred to a title block or an associated document, but there's going to be a plus or minus dimension somewhere, even if you have to look for it. The other thing, and of course in the ASME standard is long definition, but basically it's opposing points you're looking for. So a cylinder has opposing points you can measure, whether it's an external or an internal cylinder. So, a caliper can kind of measure inside out, or a caliper can measure outside in. So cylinders, spheres, widths, slots, grooves are all features of size. What isn't a feature of size is a chamfer or a fillet, because there's no opposing point to measure. Those would not be able to be controlled in the ASME standard with position. Now in the ISO standard, there's ways you can control surfaces with position, but it's outside the scope of what we're going to talk about today. Now, a bounded feature is kind of a different animal. Essentially, you're using profile with position. It's got to be an enclosed shape, and then you can use position and profile together. It's not a super common thing, so I'm not going to spend any more time than that on it. Now, position tolerances have three requirements, things that have to be on the drawing. So the three things that need to be on the drawing are: 1, basic dimensions; 2, datums; and 3, feature control frames, or at least one of these. Now, A basic dimension can look like this with a box around it, or there can be a note on the drawing that says all dimensions are basic. Datums, now this is the datum feature symbol that identifies a datum feature. The datum feature reference is in the feature control frame. It's a lot of terminology, but you can just call them datums and people know what you mean, okay? And people were saying in the comments datums are theoretical. Yeah, I know they're theoretical, but you know, for normal people, it's okay just to say datum and people know whether you're talking about a datum feature, a datum feature reference, or a datum feature symbol, okay? Now, the feature control frame, this is what's going to tell us what's going on with that feature and how we're going to interpret it and how we're going to inspect it. These elements need to be there, and they're things you're going to look for when you're interpreting or applying the position geometric characteristic. Now let's look a little bit more closely at the feature control frame, specifically for position. So the feature control frame, typically for position, this first symbol is our geometric characteristic symbol, in this case, position. The second thing we'll have is the shape of the tolerance zone. We can have diameter, we can have a spherical tolerance zone, or there could be no symbol there if we're controlling a width, so a center plane, right? Next is the value, or the tolerance value. This is given as a total. So when it's applied to a diameter, that's the diameter of the tolerance zone. When it's applied to a sphere, it's the diameter of the sphere. When it's applied to a width, it's the distance the two planes are apart in which the center plane of the feature must lie. Next up, material condition modifiers. Now, position is applied to features of size, so there'll either be a symbol here. If there's not a symbol here, then it's regardless of feature size. That's rule number 2 of the ASME standard. It just means that no symbol, the tolerance is always 30 thousandths. With the symbol, the tolerance can change depending on the size of the actual feature, and I'll discuss a little bit more later. Next up are datum references, or primary, secondary, and tertiary datum. In that order, it doesn't matter what letter of the alphabet they use. Now, most of the time people use A, B, and C, but it doesn't have to be. You can use any letters that don't look like numbers. So you can't use I or O or Q, but any other letters you can use. Now, depending on the datum feature, sometimes these will have material conditions. Now, in this case, A doesn't have a material condition, B does. B applies at MMC, which can make gauging easier. Now, if the datum feature is a feature of size, again, just like the tolerance, it's going to be regardless of material boundary, which is like analog to regardless of feature size, unless you got an MMC or an LMC symbol in there, okay? So the tolerance in the feature control frame, as I sort of mentioned before, can control a couple of different things. I would say the most common thing is the axis of either an internal feature like a hole or an external feature like a cylinder. Now, it could also control a center plane. When it controls a center plane, it will not have a diameter symbol there, and I'll put a figure on the screen for you. It can be used to control the width of something to another datum, or it can be used to control a slot or a groove. And the idea here is that the actual mating envelope for an internal feature, say we've got a slot, right? So this is the perfect part, this is the actual part. The actual mating envelope is 2 parallel planes that expand until they touch the high points. So imagine you stuff a gauge block in there, right? You go from a small gauge block to a large one and find the largest gauge block that would fit. And then the center plane of that gauge block is the center plane of that feature. And it would be need to be between 2 parallel planes this distance apart to whatever datums are there. So you'd end up with a situation where you have 2 planes. Of course, they're 3D, they go all the way through the part. And then you want to see if the center plane of the features within those 2 parallel planes, this distance apart. Now, practically on a plate, if it's a small enough groove, you just get a gauge block, you can flip the part over and use a height gauge to measure either side of this, take half of that, you can basically figure out where you are. This is less common for position, but it's still, out there controlling the center plane of a feature. The next is controlling the center point of a feature. This is used for spherical features, and you would see an S in front of the diameter symbol. This would be used, say, the only example I can ever really think of is like a trailer hitch, right? You've got a kind of spherical shape and you're looking to control the location of that sphere. Now, as far as how to inspect that, how to get the actual mating envelope of a sphere, I mean, theoretically it would be a perfect sphere that collapses onto the existing sphere. I don't know how you'd really do that on the plate. I know a CMM machine can do it with no problem, so I'll leave it right there for you. I would say it's a less common use of position. Now, there's another use, other exceptions. You can use position, like I mentioned before, with profile and create a boundary. I'll leave that to another video. The use with the axis and the center plane are the very most common, so that's what I'm going to spend time on right here. So let's move into talking about some of the particulars. Now, the basic dimensions always come from datums, which come from datum features. They're going to locate the true position. The true position is the theoretically exact location of the center of the tolerance zone, whether it's a spherical tolerance zone, a cylindrical tolerance zone, or two parallel planes. Now, the term true position is often used, you might say, hey, this is a true position tolerance. That's not totally correct, but it's out there, so I probably wouldn't give anybody a hard time for saying that, but technically this is a position tolerance. The true position is the location, perfect location of the tolerance zone. Now, position tolerances only work with datums. You have to be measuring from somewhere. So position tolerances locate things. In order to locate something, you have to, compare it to a different place. Let me show you what I mean on the board. So I've got a sketch on the board here. Again, incomplete drawing, but we've got a position, we've got datums, and we've got basic dimensions coming from the datum. So this is all on the part. Now, if we go to inspect this, we could make a gauge or put together, angle blocks to kind of form a temporary gauge that would look something like this, right? So imagine you just take three perfect blocks and stick them together. So you have a nice 90-degree corner here, and you've got your datum simulators, places to measure from. Now, the idea with this setup here is that you're going to put the part in there and be able to measure from these surfaces, not from the actual part surface. The reason is that if the part comes out like this, it matters whether you measure from right here or you measure from this 90 degrees here, right? So if I put the part in like so and measure the location of the hole in this direction from the datum simulator, I'm going to get a different answer than if I push the part up against the datum simulator and measure it like this. That's what the order of datums gives you. So we're going to make 3 points, in this case, from 3 points of contact with A, which means we'll push it up against this large flat surface. 2 points of contact with B, which means we'll push it up against datum simulator B, and it only needs 1 point of contact to lock translation for C. And then we're going to make all of our measurements from there. So the way I like to think about it is this doesn't move. The part moves around this. Now, our true position shown right here also doesn't move, right? You kind of imagine the part fitting around the true position, and then it's very important that we always make our measurements from the datum simulators, the inspection equipment. That gives you repeatable results. For the most part, your actual measurements when you're doing this on a plate, right, you'd probably be using a height gauge measuring to the gauge pin. Now, this would take a very large gauge pin, but imagine we put a gauge pin in here. We put it in the fixture. We put our height gauge on this surface, or however we need to do it. We measure to the top of the pin. We take half of it. That gives us the location in one direction. We can flip the whole fixture over and get the location in the other direction. So we're going to get repeatable results no matter how far off the actual part might be. Now, you don't have to do this way on a surface plate. A CMM will do it perfectly fine. There can be issues if you try to do it with a height gauge. Say you take a electronic height gauge and you take a point here, here, and get the middle. It's all about how you actually set it up on the plate according to the datum references. Again, the datum references don't have to be in this order. It could be A, C, B, and then you'd set the part up differently. There can be different datum reference frames on the same part. So if this part had multiple holes and one of them was ABC and one was ACB, you'd have two different setups on the exact same part. And then the next thing is, sometimes people ask, okay, well, what's A doing, right? We're not taking any measurements from A. And you sort of are. It depends how thick the part is. So a really thin part like this, you wouldn't typically flip it over and measure the gauge pin on both sides. But if a part is thick, you're going to flip it over and measure it on both sides. A is controlling the perpendicularity of the part. So if you imagine our round tolerance zone right there, that tolerance zone is also perpendicular to A in almost all cases. Okay, so that's what A does in this case, or the primary datum feature. So let's chat a little bit about material condition modifiers. In this case, it's a position, feature of size, no material condition modifier. It means that this applies at RFS. So what exactly does that mean? If we make a little chart, it just means that if the hole comes in at MMC, the smallest hole, 0.98, you have 30 thousandths position. Comes in the middle, 30 thousandths position. Comes in at LMC, the largest hole, 30 thousandths of position. Okay, so pretty straightforward stuff. It gets expensive to do it this way because a lot of times, you know, when you have a clearance hole, it's okay for the hole to get bigger. That doesn't matter so much. You just don't want it to get smaller because something, whatever's fitting through it, might not fit through it. So we have a solution for that. It's called the concept of MMC. So what MMC does is that if the feature comes in at the MMC size, you only have 30 thousandths of tolerance. If it comes in at any size going away from MMC toward LMC, so in this case, if the hole gets bigger, you get more positional tolerance equal to the difference from the size it actually is from the MMC. So let me show you what I mean in this handy chart. So at MMC, we have 30 thousandths of tolerance. That doesn't change, right? 30 thousandths at MMC. But if the hole comes in 20 thousandths too big, we can add that to our existing position tolerance. So in this case, we would have now 50 thousandths of position tolerance. As the hole gets bigger, you get more positional tolerance. If it comes in at LMC, we just subtract the LMC from the MMC, we get 0.4. We add that to the 30 thousandths we already have from over here, 70 thousandths. Okay? And that's what MMC does in this situation. For a hole, for an external feature, it gets flipped. Now, next up, we're going to talk about the concept of virtual condition. In this case, it's just the smallest the hole can be, taking into account the size of the hole and the geometric tolerance. So visually what I mean is, say a hole in a part comes through like this. if we have a pin that has to be perpendicular to this surface and fit through the hole, there's a limit. The size of the hole matters and the position of the hole matters, right? So this cylinder right here, if it's perpendicular to this surface, which is usually like a datum A or a primary datum, and we want it to fit through the hole, that's going to be smaller than either the size or the geometric tolerance we're considering. So this is known as the virtual condition, or it could be a worst case condition. So how we get this, what this diameter of this is supposed to be, is by subtracting any of these two numbers horizontally. So we're going to get 0.95 across the board. That would be the diameter of this, okay? It's a very, very handy thing, because if we can prove at inspection that a pin of 0.95 will fit through that hole when it's perpendicular to A and then, located everything else, whatever, we know that feature is good. It'll meet its functional requirement. We can't do this with RFS though, just MMC. Now, so this is handy at inspection. We can have a hard gauge that can make sure it can verify that this position tolerance is good. Then you just have to check the size tolerance and make sure the hole isn't too big. Now, I'm going to skip LMC. I've got other videos about that. Basically, LMC is opposite, right? As the hole gets smaller, you get more position tolerance, whereas at MMC, when the hole gets bigger, you get more position tolerance. LMC is used when you're protecting wall thickness, when you have, like a spokes in a wheel, and you want to make sure those holes don't get too big to where they, cut into existing material. That's where LMC is used, but this is not that common, so we'll go ahead and move on. So we've talked about what position is, the kinds of things it controls, what we're looking for. Now let's dive into how you're actually going to interpret the data you get. So if you inspect something on a surface plate, you're essentially going to get X and Y locations for the actual mating envelope. Now, these numbers are not going to correspond with this diameter. Let me show you what I mean. So say we've set the part up on the plate and we get some measurements. So what I'm saying here is you get in the setup and you're going to measure to your gauge pin from one side, and then you're going to have to flip it over and measure from the other side. So you subtract half of whatever the gauge pin is, and you're going to end up with something like this. So from the previous drawing, our basic dimension was 1 inch. So we're going to say we're 10 thousandths off in this direction and 20 thousandths off in this direction. Now, we want to compare that to the true position, right? The true position is somewhere in the middle of the part. So we want to find the variation from the true position. This is the variation from one of the datums. Now, how we do that is we're going to subtract the basic dimension or the drawing dimension from what we actually measured to get our variation in X and Y from the true position. So in this case, we've got positive 10 thousandths and negative 20 thousandths. That doesn't get us any closer to knowing whether it's within tolerance or not, because these are the X and Y's, this is the diameter. What I mean, if I plot this on a Cartesian coordinate system, we're +1, plus 10 thousandths in X and minus 20 thousandths in Y. But we want to know is if this point that we measured falls within a diameter of 20 thousandths on the true position. So the center of this Cartesian coordinate system is the true position. So we can draw a circle, and you can graphically do this, right? It's called paper gauging. You could, if you have a good protractor, you can grid this out, draw a circle, and see if the point is within the circle or not. But That's probably not super common to do it with pen and paper. I mean, you can do it with Excel. The way I'm going to show you here is to convert this point into a diameter so you can find out how much positional tolerance it actually used. So what we're going to do here is find, there's going to be a triangle in here, right? A right triangle. Pretty straightforward to figure out what that is. We know where the center is, we know where this point is, and then we're going to take the hypotenuse of that triangle and double it to give us the size of the circle that point consumes. Now, the way we do that, so we're going to enter it into this formula. So the variation in x squared plus the variation in y squared, whole thing, take the square root of that, times 2. The times 2 is this, doubling the hypotenuse. This thing right here gives you the hypotenuse of your triangle. Double it, gives you the diameter of positional variation. So let's go through the math real quick. So the first thing we do, we insert their variation into their respective places. We square each one of them separately. So it turns out it doesn't matter that this one is negative. So we're going to get 1/10 of a thousandth, 4/10 of a thousandth. We add those together first. Then we take the square root. We get 0.0223, multiply by 2. It gives us the total consumed positional tolerance is 44 thousandths. We compare that to our available tolerance, and we know that this part has failed, right? This is not an acceptable place for this hole to be positionally. Now, we might have a way out. Whenever we have the MMC symbol, right? Remember I mentioned before, if the hole gets larger, you get more positional tolerance. So with RFS, you don't really care how big the hole actually is as long as it's within the limits of size. But with MMC, you want to actually find out how big that gauge pin was because you need to know the size of the hole, and I'll show you why in a second. So let's say our hole came in at its largest size, 1 and 20 thousandths. That means that we're going to have additional tolerance. So how much additional tolerance are we going to have? In this case, for an internal feature like a hole, our bonus tolerance is the actual size of the hole, so the size of the gauge pin we use to check it, minus the MMC size. So in this case, we're going to say it's 1.02 minus 0.98, the actual size of the hole. So that means we have 40 thousandths of potential bonus tolerance. Well, it's not potential because we know the size of the hole, so it's our actual bonus tolerance. Now, we can add this bonus tolerance to what we already have. So that's going to be our total allowable tolerance. Total allowable tolerance is the specified tolerance plus the bonus tolerance, okay? So in this case, 20 thousandths plus 40 thousandths is 60 thousandths. That's how much tolerance we have. We can compare it to our calculation over here. Because of the MMC symbol and that the hole came in large, this part would be acceptable at this point. Now, you have to go do this for every hole. If you're lucky, the same gauge pin will fit in every single one, but if you're inspecting, it's something you want to keep track of. Okay, so that's how MMC can help you. Say the hole, we checked the part and the hole came in small, you could go back and drill or bore that hole out again and then send it back to inspection. So it gives you the capability for rework. Whereas if we didn't have the MMC symbol, there'd be no, unless they put the MMC symbol in there and made the hole bigger, but that's, more of a drawing change, right? So that's how the system actually works. You're taking X and Y coordinates, converting it into a diameter. Another way of thinking of the diameter is that it's the smallest inscribed circle, so it has to touch the actual point, and it's centered on the center of the true position. Now, in another video, we'll talk about composite position. Basically, what composite position can do is release the requirement for the circle to be centered on the true position. It can kind of float around and get a best fit with several holes in a pattern. So I'm going to make a part 2 to this video. I think this is already getting pretty long, but this is the basics of true position. Now, obviously there's more to it than this. You know, if you go through the ASME standard, just pages and pages of really obscure stuff. But this is what I think is gonna help you, especially if you've heard of true position, you're just trying to learn. Hopefully you found this video helpful. If you enjoyed it, please like and subscribe and leave a comment down below, and keep a lookout for a second video on this topic coming soon.